yesterday had some kind of sticking power here. So what is the first thing that we need to do whenever we write the inverse of a function? And I remember Maverick mentioning what to do first on a few of these yesterday. Yeah, switch the y and the x. So first of all, let's rewrite f of x as y. So we're going to write y equals 3 to the x plus 2. So we're going to use y instead of f of x. Then we'll swap our x and y's. And we're going to write x equals 3 to the y plus 2. All right. That's our first step there. Hey guys, let's get eyes up here. Get your notes out from yesterday. Come on up. I'll get you another one. If you need a pencil, grab one right here. What's that? I have good hearing. All right. So switch the x's and the y's, which we did. But now we have to solve for y. And in order to solve for y, we have to use logarithmic form as opposed to exponential form. So what is our next move? Actually, our next move is to write it in logarithmic form. What does this look like in logarithmic form? It'll be y plus 2 on the left. Yep. So remember, hey guys, I need everybody listening, please. Please stop the conversations. Thanks. When you are writing something in logarithmic form, it is going to be set equal to the exponent. So here is our exponent. Here's our exponent. Now what? What goes on the right side? What's that? We already have the y plus 2 over here. So the exponent becomes what we equal it to. So log base 3. So log base 3. So in subscript, right? Little and a bit down there. And then x. Good. So the base value of the original exponent, 3, goes after log base 3. Base was 3 here. Base is 3 here. We're equaling the exponent, which was here. And this is the answer to the original exponent, which we call the argument, and that goes here. Now, in order to write we're almost done writing the inverse function. We just need to get y by itself. So what do we do now? Subtract 2. Good. So it'll be y equals log base 3, and then of x minus 2. So these two should be, actually that'll end up being f inverse of x is equal to log base 3 x minus 2. All right, so we have our inverse functions, and it says to verify by composition. So we need to take f of inverse of x, or f inverse of x, and then we need to take f inverse of f of x. So we got to do the composition both ways, just like we did yesterday, to verify that they end up equaling the same thing, like we had on the first two examples. So off to the side here, I'm going to do these on the left. So to verify, we are going to write f of inverse f of x. And that is going to equal, I didn't leave myself enough room there. That's going to equal, I'll just bring it down a line. The original function, 3 to the x plus 2, but instead of x, we are going to replace x with the entire inverse function. So that's going to be 3 with an exponent of log base 3 x minus 2. So exponent right here, log base 3 x minus 2. So we replace x with the inverse function, and then we still need to have plus 2 at the end. Plus 2. And when I say at the end, that means at the end of the exponent, because 2 was part of the exponent on our original function. Are there any questions about this step here? The positive 2? So the plus 2 is that plus 2 right there. And then this 3 is that 3 right there. And then this x turned into the entire inverse function, log base 3 of x minus 2. Okay. So with our exponent, the positive 2 and the negative 2 will cancel out. So negative 2 and positive 2 cancel, which will leave us with 3 to the log base 3 of x. And we talked about this yesterday, that if you have a base value taken to an exponent with the logarithm of the same base value, a log of a base value as an exponent of the same base value initially, those are inverse operations of each other. So 3 and log base 3 will cancel each other out, and that'll leave us with x. We saw that a few times yesterday. I showed you the detailed composition on the sides as to why that works. And you're welcome to do the expanded form over here, but the expanded form definitely takes a lot more room. It does work. You're welcome to do that. Or if you recognize that you have a base value taken to an exponent of a log of the same base value, the base value and the log of the base value are inverse operations, which means they cancel. And that will just leave you with x. So f inverse of x simplifies.
Attention, please. It's time for the girls' basketball team to go to the attendance office and sign out for their game. Thank you.
F of f inverse of x simplifies to x. So now we need to do it the other way around. F inverse of f of x. So now we're going to write, I'm going to leave more room this time. F inverse of f of x is going to equal, this time we're going to rewrite this function, the inverse function, but instead of x, we're going to replace x with the original function of 3 to the x plus 2 power. So we're going to start with log base 3. And then we're going to open up a set of parentheses. And instead of x, we're going to replace it with the original function, which was 3 to the x plus 2. And then we're going to write the minus 2 after that. And again, we saw this yesterday where if you have, we don't have to have the parentheses, we didn't write them here, but if you have the same base with your log and the same base value with your exponent, those are inverse operations and they will cancel each other out, and that'll leave you with the exponent, x plus 1, and then the minus 1 after that. And again, we did the work over here to show why that is. And if you want to keep doing that work and convert it back to exponent form and do all that, you're welcome to do that. But the log base 3 here and the base of 3 here cancel each other out, which leaves us with x plus 2 minus 2. The 2 and the negative 2 cancel, leaving us with a simplified x, which simplifies to the same thing as it did up here. They both simplify to x, which means they are inverses of one another. So I want you to try part B on your own. I want you to write the inverse function, which is kind of the easy part, is to write the inverse function. And then I want you to use composition to show that they are inverses of one another. So try part B. And let's go with 4 minutes. So 2:06. I'll give you 4 minutes to work on this one. 2:06, we'll check, see how it went. If you're struggling with the composition, at the very least, try to get the inverse function right. All right, who can help me out with the rest of this problem? So we write y equals log base 7 x minus 2. Then we switch out the x's and the y's. So we get x equals log base 7 y minus 2. What's the next step? Y minus 2 is equal to, what is it? 7 to the power of x. Good. So what is the inverse function? We have one more thing to do. Y equals what? Good. And make sure the minus 2 is not part of the exponent. It just goes after it. Oh, it would be. You're right. Plus 2. Yep. 7 to the x plus 2. You're right. All right. So that's the inverse function right there. Any questions about that? Any questions about our inverse function before we look at the compositions? All right. Let's try some compositions. Do they reduce to the same thing if we try them? All right, let's see what happens. So this time we've got g of x and, oh, this one is g inverse of x. And that equals 7 to the x and then plus 2. So that's the inverse function there. And I'm going to go ahead and box those up because those are the answers to these problems. The inverse functions are the answers. The compositions are just to verify that you've done it correctly. And so if we take a look over here and let's, another line right there, we'll look at g of g inverse of x for the first one. And so we're going to take our original function of log base 7 x minus 2, and we're going to replace x with our inverse function of 7 to the x plus 2. So that's going to be log base 7, and then we can use parentheses here, plug in the entire inverse function, 7 to the power of x, and then plus 2, and then minus 2 after that. Then we can actually just cancel out the positive 2 and negative 2 because technically speaking, these parentheses aren't needed. So positive 2, negative 2 cancel. What do you notice about the log base and the exponent? Yeah, they're the inverses of each other. So log base 7 and 7 will cancel. So what are we left with? X. Positive 2 and negative 2 cancel out. Log base 7 and base 7 are inverses, so they cancel out as well, leaving us with the exponent of x. All right, next, we're going to take the g inverse of g of x, which is going to be the inverse function, with x being replaced by the original function. So that's going to be 7 to the log base 7 of x minus 2, and then plus 2. Base 7, log base 7, inverses, they cancel out. We're left with x minus 2 plus 2. Negative 2 and 2 cancel out. Reduces to x. All right, any questions there before we go on? Okay, get that written down if you don't have it. I'll leave that for another 15 or so seconds, and then we'll move on to the next page. All right, flip it on over. Here we go. So now we get to actually use some of this stuff that you might actually see in real life. So in terms of flight, use a logarithmic function as a model. So a logarithmic function can approximate the altitude of a plane over time. What is the altitude of the plane 10 minutes after takeoff? So here's our function. It says a for altitude is equal to 9,200 multiplied by the natural log of t, which is time, plus 10,000. T is time in minutes after takeoff. A is altitude in feet. So let's write our function. And it also says to substitute t, substitute 10 into t for the function itself. So there's not really anything that we need to do in terms of moving anything around in this, because we're going to get a equals 9,200 times ln 10 plus 10,000. The only variable that we have here is a, which means we can just type that directly into our calculator. So if you don't have a calculator yet, like me, come get one. And we're just going to type that in, 9,200 times ln of 10, close that up, add 10,000. What do you get? Yeah. Which, I mean, anybody ever been on a flight before? If you have, you know that the takeoff, you increase pretty quickly, and then it starts to level out after a little while. So 10 minutes into a flight, 31,183.78 feet, that seems to make pretty good sense. So let's go ahead and say A equals, it says, it's not really giving us a value to use. So let's go with let's just round to the nearest whole number. So let's say A is approximately 31,184 feet. So 10 minutes after takeoff, that's about where it is. All right. So that was kind of the easy part of this one, because all we had to do is plug in for t and use our calculator. There's literally nothing that we really had to do on that one. So how about this one? How long will it take after takeoff for the plane to reach an altitude of 35,000 feet? What are we doing this time? We're actually still using this function. We are going to have to increase the time, but we want to be as specific as we can for an altitude of 35,000 feet. So how should we write our equation first? There you go. Yep. Yep. LNT, yep. Yeah. Good. So what we're trying to do here is solve for T. Now, in order for us to solve for T, I just want to be really specific about this. We need to isolate this before we mess around with anything logarithmic. Do regular algebra until this is isolated, then we can convert into exponential form from logarithmic form, okay? So right now, this is all written in logarithmic form because it's using the natural log, which is base E. That just means log base E. And let's go ahead and just move some stuff around to isolate this first. So what should we do first to isolate that? Regular algebra, what do we do? So you mean subtract 10,000? We can't subtract 9,200 because these are connected via multiplication. Yeah. So let's subtract 10,000 first. So that'll be 25,000 equals 9,200 times LNT. Now what? Divide by 9,200, yeah. Yep. So 25,000 divided by 9,200. What does that equal? Yeah, like 2.717. That's almost E. It's interesting. 2.718-ish is the value of E. Let's just write this as a reduced fraction because it's not a nice number. So let's see. Let's do, what is that? 250 over 92. Does that reduce any further? Fraction. I'm going to put 25,000 over 9,200. 125 over 46. So 125 over 46 is equal to ln t. 25,000 divided by 9,200 as a reduced fraction is that. All right. So far we've done, everything we've done so far is like algebra 1 stuff in this problem. We haven't done anything logarithmic yet. However, now we need to work this out. So how is this going to be rewritten as a logarithmic function? It's kind of like what we were just doing with writing our inverse functions, except ln means base e. So ln is base e. This is our argument. Listen up. Anytime you have a logarithmic, this value next to the logarithm or the natural log, this is the argument, which goes by itself over here when we put it into exponential form. And this right here is our exponent. So exponent, I'm just going to go ahead and define these things here. So here we go. That's our exponent. This is our argument. Right here. Base E. That means that T, the argument, which is the thing by itself, T equals base E to what power? T's over here. Yeah, that's our exponent. So the exponent is 125 over 46. So on your calculator, the only thing we have to do on the calculator is type in E to the 125 over 46 power, have the calculator do the math for us, and we're going to say the time is approximately first of all, before we do this, it took 10 minutes to get to 31,184 feet. We're trying to get to 35,000 feet. What would be a reasonable number? 15 minutes or so? All right, let's find out. So e to the x is what we want right here, which is above ln. So if you type in second and then the ln button, that'll give us e with an exponent. Then we need a fraction, so math, scroll over to fraction, and then we can use an exponent fraction, 125 over 46. Hit enter, what do you get? 15.14. There you go, about 15 minutes, makes sense. So, about 15.14 minutes. So to climb to an altitude of 35,000 feet, it's going to take just a little bit more than 15 minutes. Cool. Or if you want to write it in seconds, that would be about 15 minutes and 8 seconds. If you want to convert the decimal into seconds, you don't have to. All right. Questions about this before we look at our last part here? And then you've got one more to try on your own, and then that's it. The back page is just a lot of extra informational stuff. So, all right, let's look at part C then. On the interval 0 to 0.337, this interval here, those are x values. Both of those are x values. So on the graph between 0 and 0.337, which would be minutes, so 0.337 minutes. So basically between 0 seconds and 20 seconds, 0.337 minutes is about 20 seconds. So by the time the plane takes off and 20 seconds into the flight, that's what we're talking about, the logarithmic function is negative. That doesn't make sense. The altitude of the plane is not correct during this interval, because the altitude of the plane should never be lower than what? 0. Yeah. Also, the plane starts I think that means at the origin, which is on the asymptote of the model. So if you look here, let's actually look at this function. Go to your y equals menu. Go to your y equals menu. Let's type it in. 9,200 times ln x. We can't use t, so we'll just use x plus 10,000. That's our function right there. Now, in terms of altitude, what was the highest value that we've seen so far for y? In terms of what we just calculated, what was the highest value of y? 35,000. So we need to have a very large range of y values here. So let's change our window. The minimum x value, let's say -10 is fine. X max, let's go to 60. Let's go for an hour. And let's make a scale of 5. That'll work for our time. So -10 minutes to +1 hour, going by 5s. The minimum y value, we'll keep that at -10. But the y max, let's go to like, I don't know, 38,000. Which means our scale needs to be about, I don't know, I'm going to say 2,000 for the scale on the y-axis. So if we go to our graph, there it is. Which, honestly, to some degree, makes sense for takeoff. But the range of this natural log function is going to continue to increase and increase and increase. Planes don't do that. They level off eventually. Right? So there'd be an asymptote, horizontal asymptote at some point, but this particular graph doesn't have an horizontal asymptote. So we would have to combine it with some other function once it reaches its cruising altitude to have it go horizontal. So there are some inaccuracies with the overall model, but in between certain time frames, the model makes sense. So listen up, thank you. Okay, let's put the phone on, thanks. In between certain time frames, altitude makes sense. outside of certain time frames, the altitude doesn't make sense. It can't be negative. It's not going to go above 40,000 feet. Planes don't generally, commercial planes don't usually go that high. So it's just talking about some reasonableness in terms of what's going on with the function. So here's what I want you to do. Part 4. The altitude A, here's the same model. Oh, here we go. Commercial planes usually fly no higher than 38,000 feet. There we go. How long will it take the plane to reach this altitude? How does a maximum cruising height compare with the model? We actually talked about that last question already, but I want you to calculate how long it's going to take for it to get to 38,000 feet. Follow these directions right here exactly, but use a different maximum height. Give it a try. Take a couple minutes on that. This is the last problem we're doing. You're gonna have a good half hour of work done today. Do you have any answers? Not yet. That's all right. Take another minute. An answer? That's what I got. Yes. So here's my answer. About 20.9. If you round it up to 21, that's fine. So it's the exact same equation as we wrote up top, but instead of 38,000 or 35,000, we're using 38,000. Subtract 10,000. Reduce the fraction, 28,000 divided by 9,200, 70 over 23. So the time is going to be e to the 70 over 23 power, which is about 20.98 or 21 minutes, depending on how you round it. So that's about how long it's going to take for the plane to reach the altitude. Now, that second question, we already talked about that with part C from the last problem. How does a maximum cruising height compare with the model? What happens in the model? Maybe go to your table of values. So if we look, here's 21 minutes, 38,010 feet. That's roughly correct. However, commercial airplanes usually fly no higher than 38,000 feet. What happens if you keep going? On your table of values, what happens to the y values? Take a look on your calculator, see what happens. Hopefully you have the function already typed in. Just go to your table and see what happens once you go past 21. So what's happening? According to our model, what's the height after an hour? Like 47,668 feet. That's not going to be what happens because they don't go above 38,000. So again, there are issues with this model before takeoff and once you reach cruising altitude, but in between takeoff and coming up to altitude that you're going to be cruising at, it's a fairly accurate model, but only within a certain set of X values. The domain is limited in terms of accuracy for the range. That's what we're saying on that. So that's your lesson. On the back here, one last question. Does it make sense that the plane is at 31,528 feet after 10 minutes, but only 35,000 feet after 15.14 minutes? So that's not what we got for 10 though, is it? We got 31,184. This one says 31,528. That's weird. Oh, you know what? They estimated early. I don't like that. So this is more accurate. Regardless, it's not that much of a difference, but does it make sense that the plane is at, let's write our answer, 31,184. Think about this for a second. After 10 minutes, it's already gone up to 31,184 feet. But in the ensuing 5 minutes after that, it only climbs another 4,816 feet. Does that make sense in terms of how you would imagine a plane going? So 10 minutes goes up that high. The next 5 minutes, it only increases by another less than 5,000 feet. Does that make sense? In terms of how planes fly? Yeah. Because when you take off, you've been on a plane, when you take off, you go pretty steep. And then as you get higher and higher and higher, your rate of increase decreases. You start to level off a little bit more. So those last few thousand feet take more minutes to gain that altitude than the first few minutes did, because you're not flying as steep as you were. So you take off, you eventually start to level off a little bit and a little bit more and a little bit more. So I would say, yeah, it does make sense because you're very slowly gaining in altitude the higher you get. Whereas the lower you get, you're gaining altitude faster. All right. Down here, this is just a summary of the different things we talked about in this lesson. So we don't need to really talk about that again. If you need a quick recap of a lot of the stuff we did, that's right here on the back page. So that is your lesson for logarithmic functions.